Generalized integer recurrences, like the 3x plus 1 problem, are notorious for profound unpredictability. Discrete chaos naturally resists being modeled by continuous, predictable geometric curves. This chaos stems directly from the mathematical tension between competing coprime bases, like base 2 and base 3, operating simultaneously on the same integer sequence. Because the numbers jump erratically between these bases, discrete integer sequences traditionally resist exact measurement using standard topological entropy calculations. Compare this to the predictability of 1D continuous geometric return maps. In continuous dynamics, space is bounded, thresholds are clear, and paths can be rigorously mapped. The Symbolic-Branch arithmetic program is a rigorous framework engineered specifically to bridge the gap between these two worlds. The framework relies on specific starting parameters, a length h itinerary, and a binary carry word that dictates the sequence of local steps. The ultimate goal of the program is to map discrete valuation arithmetic directly onto continuous geometry to extract an exact, closed-form topological entropy limit. This limit cannot be estimated empirically. Deriving it requires constructing an exact age-structured spectral gap. Determining the true entropy of chaotic arithmetic sequences requires discovering a mathematical conjugacy, a translation layer that forces discrete integers to obey continuous geometric rules. This animated diagram shows the generalized affine recurrence equation. Notice the variables a and b. These are strictly coprime integer daces, such as 2 and 3, operating simultaneously within the equation. The local recurrence produces a specific weight system, labeled here as w sub I. If we break this term down, we can track exactly how the prime factors of b accumulate at each step. Look at this tier system beneath the equation. It tracks the basic valuation. Because a and b are coprime, the weight term never picks up an extra hidden factor of b. The valuation increases in exact rigid steps as I increases. This reveals the non-cancellation mechanism of lemma 1.5. A term possessing the exact lowest valuation cannot be mathematically cancelled by a sum of any terms with strictly higher valuations. Since that lowest valuation term is effectively locked and cannot be negated by any combination of higher terms, the resulting sum is always unique to its specific carry word. This provides the proof for carry injectivity. This injectivity extends to the critical orbits. It ensures that no two distinct arithmetic branches can ever mathematically overlap, and no non-zero orbit can ever collapse to zero. This property is isolated entirely to coprime integer pairs. If bases share any common factors, the valuations collide, and injectivity breaks, and the exact structure dissolves. But as long as the bases are coprime, this rigid, non-collapsing structure scales infinitely across the entire number line without degradation. Because valuation separation mathematically forbids branch overlap, the discrete arithmetic sequence contains the exact rigid structure necessary to be formally mapped onto a continuous geometry. There is a primary structural gap in the proof up to this point. Arithmetic state variables on a number line do not natively match the bounded coordinates of continuous dynamical return maps at all. Lemma 4.15b, the centered carry conjugacy, provides the formal mathematical bridge between these two states. This number line plots are discrete integer data. The first step of the transformation requires subtracting the periodic no-carry reference orbit from the original discrete sequence. We then center the coordinates by dividing the result by the modulus m. The infinite number line morphs into a fixed normalized 1D geometric interval, bounded exactly between 0 and 1. This centering perfectly translates the discrete carry choice of 0 or 1 into strict continuous spatial thresholds. The mathematical choices are now physical locations. What emerges is a 1D affine return map. Two piecewise linear branches are plotted over the thresholded interval, and both share the exact identical constant slope of lambda. The slope lambda is a direct deterministic product of the original arithmetic parameters, specifically 3 to the power of O divided by 2 to the power of P. This guarantees a perfect concatenation property. Multi-period arithmetic sequences compose perfectly with these continuous branch maps without any deviation at all. By mathematically subtracting the baseline and centering the coordinates, the chaotic number-theoretic recurrence is perfectly locked into a rigorous, piecewise continuous dynamical system. This diagram illustrates a highly complex test case, the period 4 itinerary 1110. Its known invariant core X is demarcated here and subdivided into 3 specific overlapping domains labeled A, B, and C. The goal is to track the mass of orbits as they flow through this core to calculate the system's exact topological entropy. Applying a standard coarse Markov partition utilizing only states B and C inherently fails. Lemma 4.22 defines this as a structural obstruction. Standard partitions fail because of the degenerate channel problem. When an orbit arrives at state C, a standard partition forgets its historical origin. As this flowchart shows, the system hallucinates an invalid ghost path, immediately overcounting the compatible trajectories. Lemma 4.21 introduces the analytical solution to bypass this Markov barrier, the age-structured operator. We define a new 3-part state space. This tracks distinct finite atomic measures simultaneously across the B, C, and A pools. Watch how the mass flows. The B and C mass returns immediately to the invariant core. Simultaneously, the operator tracks the launch of new A seeds onto an external track, physically advancing step by step as they multiply by slope lambda. These specific A excursions are mathematically tracked by their exact in-flight age until they hit their strict mathematical exit thresholds. By engineering an operator that explicitly remembers the age of out-of-core excursions, we eliminate truncation errors and perfectly capture the system's exact dynamical length. The final theoretical mechanism required to extract the exact entropy is proving a spectral gap for the age-structured operator. This formula maps the spectral composition. The dominant eigenvalue, lambda, dictates geometric growth, dominating the residual R sub n term. On this spectral plane, lambda equaling 27/16 sits perfectly on the outer boundary. The mathematical noise, the essential spectrum, is trapped within a tighter inner radius. The physical consequence of this spectral gap forces the normalized ariths of the system to converge exponentially fast toward a single, unique eigenvector. This exponential convergence translates directly into the calculation of exact core cylinder count growth rates. This produces the ultimate payoff of the Symbolic-Branch arithmetic program, the exact topological entropy. A logarithmic convergence graph plots the result. The spectral radius and exact entropy limit resolves identically to the geometric branch slope. H equals the natural log of 27/16. The pipeline holds from end to end. We started with discrete block stacking, mapped them into continuous thresholds, finishing at the age-structured spectral gap. Empirical estimates have been entirely replaced by a rigorously proven closed-form limit. Spectral projection demonstrates that the turbulent behavior of integer recurrences is governed by a rigid, repeating geometric lattice.